So today I will speak about denoising diffusion models, how you can train them on incomplete satellite data. So we are interested in ocean properties like sea surface temperature and chlorophyll or altimetry. But unfortunately, a large fraction of the Earth's surface is covered by clouds, which blocks all these optical sensors. And but for many applications, you will need to have full fields. Like even if you compute the mean, you will need to have a full field. If you're just computing the mean on available data, you will bias your mean towards area where we have less cloud coverage. And also another problem is that the accuracy of the interpolated field is not something uniform then. Okay, while you can assume that the accuracy of the input data is often uniform, sometimes not, but often is the case. When you do the interpolation later on, obviously you have much precise results where you have data and less precise results where you don't have data. And here is kind of a motivating example. So what you have on the left is the sea surface temperature as observed by MODIS, which is a satellite from NASA, which and you see obviously you have missing data. You have clouds. This is the white patches there, and that's the Alboran Sea and the Mediterranean Sea. And you have classical techniques like D that can allow you to give an estimate over the full area. But typically, where you don't have data, the analysis would be rather smooth. Okay, and also you lose some small scale information. And more importantly, it is really hard from this classical technique to get a realistic error estimate out. So what we developed is to use neural networks for this. So neural networks are really interesting because they are very easily extended to multivariable variables, and also you can also train them on incomplete data. Yeah? Just by applying some scaling, instead of working with the data themselves, we divide the data by the expected error. And if the data is missing, we're just simply saying, okay, the error is infinitely large, so it will give a true zero. Okay? So that's the baseline technique that I will use in my talk, which is called Dinke, is a typical UNet. So you have your input data, processed with clouds, and then you go through a certain number of convolution layers, and then at the end you will get the actual field, but also the representation of the error. Okay, and this is quite close to what Anas was mentioned yesterday in his talk about surrogate model. So often you ask the model just to give you an answer, but you can also ask the model to give you an answer and the uncertainty. And this is also something that you can include in your cost function. And so the loss function is a bit particular in this sense because you have not only the reconstruction but also uncertainties. So and if you take the logarithm of the Gaussian likelihood, so where y is the actual measurement, yeah, sea surface temperature on the satellite, y hat is the estimated sea surface temperature, and sigma hat the estimated standard deviation. Yeah, and if you write down this conditional probability for the Gaussian, you will end up essentially with two terms. So one term is saying the neural network should be close to the data where you have it. So this is this term scaled by the expected error variance, and then again another term which is often constant if you don't consider it, but then it takes into account the logarithm of the error variance. Okay, and there's a nice interplay between both terms. So if you would not have this term, yeah, a neural network will just be lazy. If you ask him what is the temperature for tomorrow, it will probably say it will be 10 degrees, but with an error of 100 degrees. Okay, this term would be really small because it says I'm really uncertain about this. Okay, so therefore the second term is there to keep the neural network informative, saying you have to make a decision. You cannot just say you don't know all the time. And so we applied this to to seasurface temperature. Here, this is a case from the Adriatic, also Mediterranean Sea. And and it's quite easy to include other parameters that we know that are, yeah, Anas, you have a question?
Sorry, there was that last term on the loss function, the log of 2 pi.
Yeah, it's a constant. I just put it here from completeness. If you have a logarithm, you get all these 3 terms, but then you compute the gradient and everything which is constant just disappears. Okay. Okay. So when we use neural networks, fairly easy to compute, to use other parameters. So we know that chlorophyll concentration or seasurface temperature is also related to wind stress. If you have a lot of winds, typically temperature goes down. And also fronts in temperature tend to be aligned with fronts in chlorophyll. And so there's a lot of synergies between the different variables. And we were able to show that it actually helps to include these additional parameters in order to make a reconstruction of data. And also we extended this technique to not using structured satellite data. So typically seasurface temperature will essentially be images, so arrays where you have just missing data. But there are some satellite data that just give you just a point cloud. It's actually just a satellite which flies over the ocean and then measures the data along a track. So it's no longer data which is organized along a grid. But by just adapting your first layer in a neural network, you can also include this kind of information and then still get some gridded data along with an expected error estimate in return. So we validated, and it's the validation compared to independent data was relatively good. And also what is quite interesting is that we also can estimate the reliability of the predicted error. So simply by every time when the neural network tells me, okay, for this pixel I have an estimate of saying, so this is altimeters in centimeters. For this pixel I have an estimate of 1 centimeter. Okay. Now let's take all the pixels where I have an error about 1 centimeter and then compute the actual error compared to independent data. Okay. And so if both coincide, you should be perfectly on this dashed line. Okay. So what we have, it's a slight offset, but it's still a very good match actually. So we are underestimating the actual error by 4%, but to me it's quite surprising that the neural network was able to give a really reliable error estimate. And that is something that's actually very hard to get from traditional methods, because a lot of assumption goes into how the error is. So if you know about optimal interpolation, which is quite commonly used in oceanography, there's a lot of assumption that goes into the how the error is correlated in space, and this will actually give you a usable estimate of your of the variable, of the reconstructed variable, but it will actually not be really reliable on the error estimate. Okay. But there's a big limitation that we have here. So far, we have an error per grid cell. Okay. So we have an image as an input, yeah, with clouds, and we'll get a full image at the output, and then for every grid cell, we get an error estimate. Okay. But as once you do something on this reconstructed image which involves different grid cells, you need to know how the different grid cells, how the error in different grid cells are correlated. So a very simple example would be just computing the mean. Okay, if you assume that there's no correlation between the different grid cells, just computing the mean, it will give you it will severely underestimate the error in your mean if you computed all grid cells are statistically independent. Okay? So it is very important to not only give you the error for each point individually, but also tell how this error is correlated in space. Okay? And in ocean modeling, or in particular in data simulation, so when you combine ocean with ocean model output with data, there's a technique which is commonly used, which is called the ensemble Kalman filter. You're typically not running your model once, but you're running the model several times. Yeah? And then the spread of the model gives you the uncertainty, and it also gives you how the different grid points are related. And this is actually what also all the weather services are doing. So today, if you look in your app and seeing tomorrow there will be a 10% chance of rain, it just means that the ECMWF or any other weather service has run 50 ensembles, 50 has run the weather model 50 times with slightly different initial conditions, and in 10% of this ensemble simulation, it was raining. So using an ensemble approach allows you also to take into account this uncertainty. Okay, and we're using here a denoising diffusion model, which is a really as a new type of generative model. It's really fun to play with it. So you can generate images based on text, and they are really good at generalization. So they learn what is the structure in an image, and then you can guide the generation of the image using text. Okay, so I'm pretty sure there is no penguin on an astronaut penguin on Mars in the training data set, but it still managed to combine this information. Okay, and the math behind the denoising diffusion model is actually quite elegant, I think. And so you start with an image, yeah, and then you add noise to it. And you add noise to it just a little bit in a large number of steps. So think of 1,000 steps or 100 steps where you corrupt the initial image with noise. And what you get in the end is a completely noised image. Okay, you're destroying all the information. So that was the easy part. Destroying information is easy, just adding noise. Okay, but then a denoising diffusion model makes the backward steps. Okay, but not from a fully noised image to a realistic image, but only from one step to the previous step. So these are a really large number of steps. Think of it 100 or 1,000 sub-steps. So when you just add a little bit of noise, the problem gets much easier to remove the noise. Okay, and this is really profound consequences, because when you generate this image, yeah, and so think of your neural network has 10 layers and you have 1,000 steps. The image generation use effectively 10 times 1,000 neural network layers. So you have a huge neural network, very, very deep neural network with shared weights, obviously, but to generate an image. But when you train the neural network, it will be just from a noisy image with a little bit, removing just a little bit of noise. Okay, so this helps a lot to train really deep neural network, and what is also something called the vanishing gradient problem. Okay, any questions about this? Okay, yeah.
So the network that you use from one step to another is the same network?
Yeah, it's exactly this. Exactly, it's the same network with the same weights. Yeah, it's not, but you give it the diffusion time in some sense. The network knows, okay, now I'm at step 50, and I have to go to step 49. Okay, so it knows at which step it is, but the weights are the same. Exactly. Yeah, good question. Okay, and so we trained this on chlorophyll data of the Black Sea. So we used all the data of the Black Sea and then validated on this area. So, and this was the first time we worked on this kind of network. So the size of the image are fairly small. So this is just 64 by 64 grid cells. And as usual, we are training on about some 15 years of data, and then validating on the last years of data. So the validation and test data set is independent from the training data set, as you would expect. Okay. So now the traditional diffusion model works. You train the traditional diffusion model by using complete images. Okay. But for ocean data, you never have complete images. You could use them from a model, but if you want to train a diffusion model, or you could use it from a hydrodynamic model, but if you want to train a neural network with satellite data, you will always have cloud. So you have to think about how to include the fact that you have missing data already in the training data set. So what we use, we have this original data with already some clouds. Okay. We add even more clouds. We're just taking the cloud mask from another image, and so we have this image with combined cloud. Okay. And then everywhere where you have cloud, we replace the values by just noise, random noise. So meaning something is clouded, it's just saying you don't know anything about it, so it is just a noisy, just a random variable, instantiation of a random variable. Okay. But in fact, when in traditional diffusion models, you assume that an image, yeah, is as a fixed state of degradation. Yeah. Here we assume that every pixel can be a different state of degradation. Okay. So you have some pixels here which are non-degraded at all. They are in fact already very at the start of the diffusion pipeline, and one are completely degraded, and one are just partially degraded. Okay, so that is the trick that we use to train the neural network with noisy data, is assume that every pixel can be a different state of degradation. Yeah.
I find this really interesting. So usually with the diffusion, you're adding noise to corrupt each time, but it seems like one of the things that could be done here is like the actual cloud mask itself could be the noise that corrupts the original, because the goal is to take an image that has cloud cover on it and recover the original image without the cloud cover.
Yes.
And so instead of corrupting it with noise, are you corrupting it with a random cloud mask every step? Is that what's happening here, or?
So the additional cloud mask, that's just added once. Okay. Well, it is, and then when you go back, when you do the reverse diffusion, this cloud mask doesn't change. Okay. So in this step, it is fixed. Okay. But during training, you will make other combinations. Okay. And so the idea is that you have this image, and then you have a different noise level for every pixel. Okay. And then you are asking the neural network to remove the noise. Okay. And the loss function, you can only evaluate them at the pixels where you have the ground truth value. Okay. And so when you have your neural network trained, then during inference, you take this image, every cloud is just replaced by random noise, and where you have actual data, you're saying these pixels are already totally uncorrupted. Okay, these are already at the step 1 of my reverse diffusion pipeline, and the other are at step 800. Okay, and then you're asking to go just one step back. Okay, and so on, and then you will see that naturally a realistic-looking image emerges, because you're asking for every pixels where you have some noise, just remove a little bit of noise. Okay. And so, and the nice thing is, once you have an ensemble, you can always compute the mean and things like standard deviation. Obviously, when you compute the mean, you will smooth out all this fluctuation. This is actually a desirable property. If you ask me what is your most likely estimate for chlorophyll or for temperature, then, and if you have an ensemble, then you should take the mean. Okay, because this minimizes your error. But once you have this sample, you can easily now use this sample to compute other statistics as well, like the standard deviation or also some derived quantities like if you're looking at fronts and things like this. So you can easily propagate this uncertainty in a Monte Carlo-like fashion to other approaches. Okay. And so there are different ways that we can validate this this result. So we're looking here at the variogram, which tells you essentially how similar the field is between two grid points. Yeah? And if this distance between two grid points goes to 0, the variance between them should go to 0 as well. So that's the variogram. And it's how quickly they go to 0 tells you how much information you have at small scales. Okay? And we see here that in blue is original data. In orange, that's the Denoising data, so the traditional UNet. And we see that we're losing a lot of information at small scales. But with the diffusion model, we can actually recover a lot of this variance. It's not as variable as original data, but it's already much better. Another thing that we can do is actually, and this is done quite often in metrology as well, is to compute the talagram diagram, and it essentially tells us how reliable your probabilities are. Okay, so if I say the probability that the chlorophyll will exceed a different threshold by, say, 20%, can I trust this 20%? Or did you make it just up out of thin air? So how reliable this estimate is, okay? So the talagram diagram is a bit mathematical, but if you, there is a graphical representation, if you have a flat talagram diagram, it means that you are, so if all these blue arrows will be the same height, and then it means that your probability are perfectly reliable. Okay, and here we are not actually too far away from it. We're quite happy about it. So you can easily think of if you have hundreds of an ensemblement of hundreds states, yeah, and you took the median state, yeah. And then your actual measurement should be 50% lower and 50% higher than the median state. Okay? And so what the talagram diagram is just not losing the median state, but it uses all of these quantiles for every ensemble member. Okay? And just this is an example with Denoising, which can also provide an error estimate, but it's not. So the diffusion model is really much more reliable in terms of the accuracy of the ensemble. Okay, so here this is just an animation about where I applied this technique to a larger data set, which is mode surface temperature for the whole globe. So it's trained really on the whole globe, and I here use larger images. Before it was 64 by 64, now 125 by 125 to give more context to the reconstruction. So what you have here is the original data, and then the data where so original data with some clouds. In this case, quite few. And then we added even more clouds because we want to know how the method is actually doing. And this is the data were replaced by noise. And then we're asking the neural network to, during this reverse diffusion, to at every step reduce a slightly bit of noise. And then we have a quite realistic looking image at the end. And it's not only realistic looking. When you compare it to really quantitatively with RMS error, you can see actually it's actually better than Denoising. Yeah, Anas?
So just to kind of clarify the workflow, you start off with an image that has some kind of cloud cover, and then you have a mask for where that cloud is, and then that mask allows you to add. You can only add noise where the mask is. You don't add it anywhere else.
Yeah, during inference, yeah.
And then you go through your diffusion steps and corrupt it, and then you go backwards, and then you pull away the noise, and which the mask doesn't exist anymore, only the noise does, because the mask only says where the noise should be.
Yeah, exactly.
And then when you go backwards, you decorrupt it by denoising it.
Yeah, exactly. So the mask tells you how where you should put the noise. Yeah, exactly. Okay. Okay. So in conclusion, we had another question. No. Okay. So in conclusion, so I showed two methods. So the Dinkai with a traditional UNet, it is trained in a classical, I would say classical supervised way. You have your image with noise, with missing data, and then you add even more missing data and then try to recover the data under the clouds. And the diffusion models actually gives a better accuracy than Dinkai, and it gives also a reliable ensemble, so which is also statistically reliable. And this was quite interesting to see actually, that you can actually trust the different ensemble that is produced, and this is quite important in order to propagate uncertainty. So you don't. So somebody who wants to use the satellite product later on, okay, instead of using just the ensemble mean or just a single reconstruction, the idea is that any other processing step which comes later will also operate on different ensemble members, and then you naturally get also an uncertain estimate of the output. Okay, so if you want to identify fronts, okay, in some ensemble members the front is maybe slightly offset, and then later on you can see, okay, in some places the front was always located in this location, so the uncertainty in my front estimate is quite low. But in other cases, the front is shifted, so this can also be represented. And also, really nice thing that you can, you no longer, you can, in the ensemble members, you can retain small scales. They're not smoothed out. If you take the mean, obviously it will smooth out because you don't have information about small scales in the actual data, but every ensemble member individually contains this small scale information. And so we have two papers here where you get much more information, particularly if you're interested in the more information about the validation. And everything is on GitHub and written in Julia. And so just to set the stage for what's coming later on, so I made some toy models about ocean modeling, and I don't know about you, but in our university, it's not always easy to motivate students to get interested in ocean modeling. And so I made some animations, or they're actually demos, so that run in your web browser. That's actually Julia code, which is compiled to WebAssembly, and then we can run it directly on your web browser. And you can. This is, I think, something I showed already last year. So you have a flow which goes from the left to the right, and then you can perturb this flow by adding other islands to see how it changes. And something what I made recently. So this is a simulation of the equatorial ocean. So the equator is really you can think of the equator as the middle line in the ocean. So this line would be the equator, and you have an initial perturbation. And what happens at the equator, very interesting thing happens, that this initial perturbation breaks down in two different waves. This is a Kelvin wave, and this is a Rossby wave, and this is the driver of, for example, the El Niño weather phenomena. And you can also play around here. You can say, let me perturb this Kelvin wave by a coastline. And you see, so if an equatorial Kelvin wave hits a coastline, actually it splits up, and one is going northward and one's going southward. And this is essentially due to the Coriolis force. A lot of things which happens in the ocean, which are really a bit counterintuitive, it's due to the Coriolis force, and it's a really quite interesting thing. Yeah, and so there are other models here that I just implemented. So this is smooth particle hydrodynamic models, and it's also implemented in pure Julia. And then you can actually WebAssembly is a support backend in Julia, and then you can compile it down to WebAssembly. But it's a bit tricky because only a small subset of Julia is supported in this way natively. Yeah, so if you want to play around this is the URL, tiny URL/model font, so it's easy to remember. Yeah?
I'm curious though, for like, for example, with the Gray Scott model, I saw in there, like the Gray Scott model is a classic, like, diffusion kind of one where you normally would want to use implicit methods, but I assume that you wouldn't be able to compile anything with loss too also, right? So how did you handle that part?
Yeah, so I actually tried to compile BLAS into WebAssembly. It's just a nightmare. I did not succeed it. And it's really, really difficult. And so I used an explicit scheme here. Yeah.
Okay, so they're all just explicit schemes.
Yeah. But actually, in this case here, and so these are the waves, the surface gravity waves in the ocean. And if you, for example, so this is the external wave, yeah. And if you are just having a look at the other wave number, what you see here are the internal waves. So if you remember Giles' simulation about the internal waves, yeah. So this is the typical vertical structure of the internal waves in the ocean. So this is a cross section. So one dimension is the horizontal dimension, one is the other, the vertical dimension. In order to compute this, you need to compute the eigenvectors of a matrix. And yeah, that was the reason why I tried to compute BLAS to WebAssembly, but it's really difficult. So I use a very simple scheme. Yeah?
Similar to your previous tool, I think for DIFA demo, you also had a web page to play around with DIFA.
Mm-hmm.
My question is related to that. How do the previous models you showed in terms of the diffusion model and also the convolutional model, how do they compare to DIFA and D?
Okay.
And also maybe comment on the performance of all these models. How long do it take to train? How long do it take to run?
Yeah, very good question. So the DIFA model is a kind of classical model, and it is much faster. Doesn't need a GPU, and is, I would say, quite robust. But it's not easy to incorporate, for example, other parameters. So it's difficult to do a multivariate analysis with it, and the error estimate is not so good that you get. The error estimate is just a way to say, okay, in this area, the error is so big, I probably should not show it at all. So it's rather used for masking. So the neural network, takes much more time, and it also needs much more data as well. Okay, so if you have a lot of data, I think it's worthwhile to try the neural network approach. But if you have few data, and I think it's better to use DIFA and D, classical method. Okay. Yeah, Anas?
Not related to the images, but just to the diffusion model. I noticed that with the folks here, that the common problem is there's real data, but it's not enough at the scale that you typically would need to train a large neural network. And so in those kinds of scenarios, typically what is usually done is you find some kind of useful auxiliary task. You can kind of sample data from freely, and then once you train something, you kind of use that as a backbone and then fine tune. And I was thinking about the mask that you were showing earlier approach. And what I find fascinating is that you have the image, you add a mask, and you only add nodes where the mask is. But curiously, there are different variations of diffusion models where you don't corrupt with noises, but you corrupt with special kinds of masks. And what came to my mind was that it appears that you can actually take an image and corrupt it with random cloud masks over time. And it would be fascinating to see if you had some kind of basic simulation which you could take as a ground truth and corrupt it with a cloud mask over time, and then trying to reverse that it would be an interesting auxiliary task which you can then jumpstart onto the real data later on.
Yeah, that's true. That's true. And there's I've seen one paper who mentioned that the task of corruption can be very generic. So as you manage, you can corrupting by adding clouds or or any other corruption task actually can be used in the diffusion model. And it was indeed when you're working with incomplete data, it is actually quite natural to consider the cloud coverage itself as the corruption. Yeah.
Yeah, and it seems like it's a great starting point because you don't have to rely on real data to start your training. You can take some kind of basic simulation of temperature distribution or whatever it was that you were interested in, and then use that as a starting point. You can easily corrupt it in the natural way that you would expect to understand the problem, so that there's cloud cover, it's corrupted, and we need to remove it. You can do that over time. And then it removes your data problem because you have a simulator that you can query for free and have a good, strong starting point, have a starting kind of understanding what the modality is, and then with real data, you can then fine tune and not necessarily need that kind of large scale that you typically need if you were to start from scratch.
Yeah, that's true. That's true. So transfer learning can help a lot here. So I tried a bit this approach to see what you can do only using data. So not to because the result later on sometimes will be compared to a model, to validate a model, and sometimes you don't want to have this kind of inbreeding where what you call data is actually also influenced by model. So sometimes you would prefer it to have so separate.
But in the fine-tuning case, you would not use a simulator as a validation. You would actually take your data and split
Yeah.
it and then use it. So
That's true. That's true. Yeah, Chris?
Yeah, I was wondering if you go back to your slides.
Sure.
And if you go a few slides back, one slide forward again, right to this kind of conclusion here, right? So I want to go back to reliable ensemble of possible reconstructions and propagate the uncertainty, right? How do we know that that's actually reliable? I mean, because here's my real question here, right? So when we're learning functions, say with the neural network, right, we're guaranteed to have some sense of, if you have enough data points, this is going to converge to pre-approximating the function, right? Now in this context, you have something that is generative, right? It's generative in a way that it is giving you probabilistic results with some uncertainty, right? Do we have any guarantee that as we get more data points, that uncertainty that it is converging to actually has the same exact probability distribution as the uncertainty from the actual model, or is there no sense of that guarantee that it's actually giving you the exact same probability distribution, just one that maybe looks empirically like it?
So actually we validated the uncertainty empirically using this telegram diagram. Okay, so just by having this ensemble of reconstruction, you can see you can essentially order your ensemble members from smallest to largest, and then you look where your observations fall into. Okay, and then you increase the count for every bin. Okay, and if your ensemble is well behaved, is reliable, you should fill all the bin equally. Okay, so this is a graphical way to represent the.
And I followed you through this to say that empirically you're able to show that this method is able to in this context seem to reproduce uncertainty, right? My question is, but do we have a theoretical guarantee that this method, if you do have enough data points, is supposed to actually converge such that the probability distribution is the right one, right? Not just empirically, but do we have like this convergence proof to be able to say, oh, and I know that if I have enough data, it's actually supposed to have this property.
yeah, that's in the original thing for diffusion models. Okay, they walk through the process that in the limited data, recover the original modality distribution. So it's part of the diffusion formulation.
Yeah, so if we have a theoretical proof, so there are some assumptions in the diffusion paper. So the actual cost function that you want to optimize is not tractable. So they're computing something like a elbow lower bound value of this cost function, and they're using this. So there are some approximation into it. And but intuitively, I think when you give what you want to have is the field with less noise, and by applying this denoising process, in the optimal sense, so if your neural network is really optimal, it should really span all the probabilities. Right? Because if it does not span all the probabilities, yeah, it's not really really optimal. It's not really it did not really the right thing during the denoising. But really, for mathematical hard proof, unfortunately, I have to pass.
I'd just be scared to kind of take this and say, you know, when you say reliable uncertain propagation, I would think that you mean like, oh, you have an unbiased estimator, right, in the statistical sense, right? And for me, it's kind of hard to kind of take the jump and say, oh, I believe that this is an unbiased estimator, right? I believe it's an estimator of uncertainty, right? It gives you some kind of measure of it, but to know that it's an unbiased estimator, I think is a bit of a jump.
Yeah, yeah. So mathematically, it's not. I cannot. I don't know if it's really proven mathematically, but empirically. So we're using this telegram diagram, and in the paper there's another score that we use, the continuous rank probability score, which is also used in meteorology, where you can estimate the probability. But in practice, when you're doing weather forecasts, there is no mathematical proof either that your weather model will give you all the range of possibilities, simply because you don't know what is the uncertainty, the true uncertainty in the initial condition. You just knowing from experience that well, when I start my model with this kind of initial condition, I should also perturb in a different way because my initial condition is not perfect. So practically, there are a lot of other things that we don't know exactly about uncertainty. Okay. Thank you so much.